Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
This time we'll analyze a sliding box on a surface that has friction using the conservation of energy. The box has initial velocity of 5 meters per second at the bottom of the ramp. And first of all, we want to know, A, how far will the box travel up the ramp? So we're looking for distance d. And then in B, what is the speed when the box starts to slide back and comes back to the starting point? Of course, the final velocity would be the same as the initial if there was no friction, but the friction most likely will slow it down. So let's see how we go about this. Here I have written out the conservation of energy as shown in the overview video, and we can start working on this. So let's clear this up a little bit. We don't need all these terms. First of all, there is no elastic potential energy in this problem. We have no springs or anything like that, so those will be taken away. Also, we've defined our initial height. That's 0, where we start from. So we don't have gravitational potential energy either in the beginning. And what else? That's all we need for the second part. For the first part. And of course, the velocity at the top in part A is 0 because it stops there. So we only have this much left for the part A. Okay, and now the question is, what is the V other? So that is the work done by the friction. So if we have a free body diagram, gravity is of course down. Gravity has 2 components, like this. And then we also have friction against the direction of the movement. So that's going to be mu times n, and the n is perpendicular to the surface, like this. And so what is the work done by the friction? Let's call this F mu. It is the force time distance, so if we write this out again, it's going to be F mu times the distance it covers, d. And then all of that will be translated into gravitational potential energy. But now we have to be careful with this sign, because the friction is doing work, or the work done by the friction is negative because the direction of the friction force is opposite to the displacement. It is, of course, negative, like this. The inclination is at angle alpha, and that lets us first of all express the final height h2 as a function of the distance covered d. So h2 is just going to be sine alpha times d. And we have the same angle alpha here. due to the incline. And from this relationship, or we are interested in the vertical component of the, or the perpendicular component of gravity. So that's going to be mg then cosine alpha. And we use this relationship, or Newton's first law, because there's no acceleration in the direction perpendicular to the surface. We know that n equals mg cosine alpha, and hence the friction force, which is mu times n, must be mu times mg cosine alpha, where the mu is the coefficient of friction. Let's give that a value 0.3, for example. Now, plugging these two terms in, half times m v1 squared minus the whole shenanigan of f mu minus mu mg cosine alpha times d equals mg, and h2 was sine alpha times d. First of all, the mass cancels out, so that doesn't affect at all, or it's same for the all objects regardless of their mass. And we have half times v1 squared equals, on this side we have dg as a common term, so sine alpha plus mu cosine alpha. And from here, solving for d, divide all of that to the other side, we get v1 squared divided by 2g, and then this term with the trigonometric identities. And initial velocity was 5 meters per second. That's squared, divided by 2 times acceleration of gravity, and then sine of the alpha, we have 30 degrees, let's say. So sine of 30 plus mu, which is 0.3, cosine 30 degrees. And it's about 1.67 meters, or with 2 significant digits, 1.7 meters. For part B, we apply the conservation of energy again. And initially we have just the initial velocity, and hence kinetic energy only. And now the friction doesn't work, that's the W other, the other work, and it's also negative, so it's 2 times F, and times the distance, and it's 2 times because it comes up and then comes down. And the final position back to the starting point, it only has again kinetic energy. Let's call this V3. If point 2 is here, then point 3 is again back down. And we know what F is. Its magnitude is constant, like we solved here. So we can write half times m v1 squared minus 2 times F mu mg cosine alpha d equals half times m v3 squared. And again, m's cancel, and let's multiply everything by 2 to get rid of those halves, so we get v1 squared minus 4 mu g d cosine alpha equals v3 squared. From here we can solve v3, square root of v1 squared minus 4 mu g d cosine alpha. v1 5 meters per second squared, or v1 squared is 5 meters per second squared minus 4 times mu 0.3 g 9.81 meters per second squared. D is now 1.67 meters one way, and cosine of 30 degrees. And that gives us 2.8 meters per second as the final velocity back at the starting point. Significantly less than the 5 meters per second to start with, and that is all due to the work done by the friction.